tool in doing soil sample studies as the rover was driving through various terrains. Well, the problem with that design is as they were driving over hard material, stress fractures were building up opposite those points on the wheel. So, and that was causing structural damage to the wheels. And over time, the wheels on Mars Science Laboratory have suffered some fairly significant damage, and they have to be very gingerly treated down when they're driving over hard rocks. So the new wheels on Mars 2020 were redesigned. There's no open gaps in the tread design. In fact, during the lifetime test in which they drove the wheels over the hardest material that was identified that the MSL rover was driving over the lifetime of MSL, there was no significant damage to the wheels or actually any significant wear. So that's, you know, a lot of components are new, upgraded. The nav cams and the has cams are newer generations of cameras, and even things like SuperCam and Mastcam-Z, which are heritage on cameras that are on MSL right now, are employing new technology as well. So I'm just going to kind of briefly go through all of the instruments. The layout shows you a picture of where it is on the rover. In the upper right-hand corner, it shows the rover, and the yellow components are the electronics, the actual camera or instrument, and other components that are all part of the instrument. So Mastcam-Z itself is comprised of a left and a right camera. They're identical in design. On MSL, the focal length on the left and the right were different. On Mastcam-Z, they both have a variable focus zoom capability, so they're nearly identical. The only difference is in the filters. Within the body of the rover itself is the digital electronics assembly, which is the computer that drives the cameras, and it's connected through a ribbon cable from the mast down into that digital electronics assembly. And then towards the tail end, RTG, there's a little gnomon that is our calibration target, and we use that for taking calibration images so that we can properly calibrate the images that we acquire. Okay. SuperCam, also on the turret, is a camera with a laser, and it does also Raman spectroscopy. So it can shoot a laser at a rock, create a plasma stream, and then using the Raman spectroscopy, actually get a chemical composition. So while it's a much bigger camera lens, it's the Cyclops looking lens, it actually only looks at a very small piece of the surface of Mars when it's shooting its laser. It also has electronics which are located within the chassis. Most of the electronics for Mars 2020 are located within the chassis for thermal reasons, to keep them warm, because night times on the Martian surface are very, very cold. On the turret, on the end of the arm, we have an instrument called Pixel, the planetary instrument for X-ray lithochemistry. And this basically does X-ray fluorescence. So what they do is they find an area, we'll find a rock or a portion of the surface that we want to analyze with Pixel. they'll move the rover close in into the right position so that the rover arm can move out and then place pixel within a couple of inches of that area that we want to study and irradiate it with X-ray fluorescence and then gather the elemental chemistry of that location. Because it is on the turret, it sort of precludes any of, when Pixel is running, none of the other instruments on the turret arm can be operating at the same time. However, any of the instruments that are on the mast, like Mastcam-Z or SuperCam, can be operating at the same time. And in fact, during operations for MSL, the Mastcam instrument is often used for taking images of what's called the workplace, the area of the rover that's in front of the rover that we call the workspace that we're going to put the arm. We take images with Mastcam to create digital terrain models and use those terrain models to accurately move the rover and move the arm into the correct position for analysis. So on Mars 2020, Mastcam-Z will do much of the same kind of work as Mastcam does on MSL. SHERLOC is another instrument that's on the turret arm. In fact, the turret on Mars 2020 is so much larger. There's so much instrumentation on there relative to MSL that they actually had to put a weighted bar on the back end of Mars 2020 to keep it from tipping forward when the arm gets extended fully. I'll point that out when we see another picture. And this does ultraviolet Raman and fluorescence spectroscopy. And so most people are familiar with camera, and spectroscopy is a science that basically looks at the chemical signature of rocks or whatever sample that you're looking at and is used to find chemical signatures of that material. Because this is ultraviolet, it's looking at the wavelengths that are in the ultraviolet spectrum as opposed to visible that like Mastcam-Z looks at, and mostly in the visible, slightly into the UV and slightly into the infrared wavelengths. So again, this is the turret instrument, and so we move the turret into position for SHERLOC to detect organics and other chemical material.
Ernest?
Go ahead.
Are those diode lights that are around the perimeter of that camera lens?
The little yellow?
Yeah.
They might be. To tell you the truth, I'm not that familiar with most of the other instruments, but it very well looks like they are diodes. I can check that and let you know, but they keep us busy enough on our own instrument that a lot of times people are like, you don't know about the other instruments? I'm like, tell you the truth, I'm so busy with my instrument. Sometimes I don't know what's going on with any of the other people. But I'll check that. It very well may be part of the design. Watson is another instrument, and you'll notice that in the image on the left, Pixel is the little sort of cylindrical thing sticking out, and then the upper white flap is Watson. And Pixel and Watson are actually, SHERLOC and Watson are actually meant to work in combination with one another when we're looking at a particular region of the surface. And Watson does topographic imaging of the microscopic work area that SHERLOC is going to be looking at, so that when we get the analysis back, we can place it in context within the scene that Watson has acquired. And this is all important because as we drive around the surface and we're looking at outcrops and doing these analysis, it's all with the purpose of finding ancient microbial life or evidence of that life. And then if we find something that might be suggestive of that ancient life, actually sampling it. And so we want to have as much information of that outcrop before we sample it. So we have a lot of instrumentation that gives us a very high resolution context, both within the turret instruments and what they're looking at and what we're looking at from the mast on SuperCam and Mastcam-Z. We also have an instrument called RIMFAX, which sits on the back side belly of the rover. And as we're driving along, this is a ground penetrating radar. And as you can see from the little cartoon element, it's firing radar into the subsurface, collecting the signal, and then imaging the subsurface. And this is comparable to ground penetrating radar that we use on Earth to look at the strata below the surface and looking for contacts of material and differentiating the subsurface. And this is a new instrument. We haven't really been able to look at the subsurface on Mars. InSight landed, it was a recent mission in 2021 that landed on the surface and had put a heat probe and a couple other instruments into the subsurface to look a little bit at what the subsurface material, how it behaves and what it's made up of. But RIMFAX is going to give us a much better idea as we're driving around sampling to actually get these profiles of our drive path as we're driving along. So a lot of times as a geologist, you see outcrops, you see material, and you really want to know what's in the subsurface. So RIMFAX is going to give us the ability to see some of that material that we haven't been able to see before. And again, it's on the backside underbelly below on the chassis. META is on the mast, and it's composed of a couple of components that stick out at orthogonal angles, and it has an electronic box. And it's basically a environmental analyzer. And so it's going to be looking at things like air pressure, air temperature, wind speed. So you can think of it as a mobile weather station on the rover. So wherever the rover goes, we'll be able to collect actual weather information of the conditions on the Mars surface. On MSL and other missions, we could approximate the temperature based on temperatures from the rover itself or the spacecraft itself. But a lot of the conditions, like the air pressure and wind speeds, were something that we didn't accurately measure. So this is going to give us another piece of information in this process of getting ready to send humans back, of actually understanding the atmosphere on Mars in a much more intimate way that we haven't studied so far. MOXIE is in the chassis, and it's a oxygen in situ resource utilization experiment, which is a lot of big words to basically say it's going to look at the atmosphere environment that the rover is currently at, and it's also designed to do an experiment where it's actually going to attempt to generate oxygen from the raw materials in the atmosphere. It doesn't generate a lot. It's just sort of a proof of concept. and it also records a lot of atmospheric information along with meta. So between those two instruments, we're going to get a lot of information about the atmosphere. And in fact, Mastcam-Z also does atmospheric studies by looking up at the sun, and we can measure something called tau, which is a measurement of the lofted dust particles in the atmosphere of Mars. And as you know, recently, within the last couple of years, there was a global dust storm. And so we can measure the amount of dust that's actually lofted in the atmosphere by looking at the sun with these tau information. So a lot of the instruments actually do a lot of different duties in addition to their primary roles. And of course, the big thing is sample collection and then eventually caching those samples. So the mission profile currently is to drive around, investigate the Jezero crater area, find suitable samples, and the primary goal is, of course, trying to find these ancient life or evidence of life. It's also looking for key geologic information recorded in the rocks of the Martian surface. So not all samples will solely be samples that contain evidence of life or possible evidence of life. We'll collect samples at different locations. Those will all be cataloged, and then caches will be created at different spots on the surface as we go driving along. The idea for that is so that we don't keep all of the samples, and should we have a mechanical failure of the turret later on in the mission due to whatever reason, we don't lose the ability to get the samples out of the rover and onto the surface. So much like Apollo 11, one of the first activities the Apollo 11 astronauts did was grab what was called the contingency sample, which was immediately to scoop up a little soil and some rock samples, throw it into a sample bag, and put that into the lunar lander. So if they had to take off from the surface of the moon due to some unforeseen issue, they would at least have a little bit of the moons to take back. So the idea is we cache them. It hasn't been decided how many caches that we'll create. Those are topics that are currently in discussion as they're working through the design of the follow-up mission that will be going to retrieve those. And you know, each one of these instruments could be an hour-long talk on their own. I couldn't give them all sampling and caching. The whole assembly has a whole series of processes and instrumentation to ensure the sample we gather is complete and contains the material that we're looking for, and that it gets sealed up properly to endure until it gets collected at a later point in time. So as I mentioned, we launched. We've launched. We're currently in the cruise phase, and this is a picture taken at Kennedy Space Center of what we call the clamshell. So this entire assembly closes up so that you can't see the rover. The bottom portion that's sitting in the cradle is the heat shield that will protect us as we enter the atmosphere of Mars. And then as once we've slowed down, that heat shield will drop off. You can see the large, there's 4, and there's another set on the other side of rocket bells that are the downward facing thrusters that will do the final termination of slowing us down. So the heat shield, in coming through the atmosphere, slows us down a considerable amount. The thrusters will take over, get us down close enough to the surface so that the sky crane, which the rover is attached to in that upper assembly, will lower it just right over the surface, and then those tethers will be broken and the rover will be put on the surface of Mars. The upper thing that looks sort of like a carousel with little flanges coming down, that a lot of that is the electronics for the cruise assembly, and it will drop off as we approach the atmosphere of Mars. So only the bottom two components will actually go through the atmosphere. And that was the last time we saw the rover, as it was closed up and then placed in the fairing for launch. Now, the Mars 2020 landing looks a lot like the MSL landing. They have what JPL likes to call the 7 minutes of terror, which is the period of time when that clamshell assembly is going through the atmosphere of Mars. And because it's creating a lot of heat and ionization, there's no communication with the spacecraft during those 7 minutes. At the end of the 7 minutes, we expect to get acquisition of signal from the spacecraft that will let us know that it's in the final stages of delivering the rover to the surface. Now, one of the upgrades that Mars 2020 has over MSL is it has terrain navigation software. So where MSL was basically targeted, and once it was committed through its atmospheric entry to the landing ellipse, Mars 2020 can actually take images of the incoming terrain that it's approaching and make a decision whether to continue with the landing sequence or divert if necessary, if the landing area is not hospitable for the rover. And this is, again, an upgrade from MSL. And again, harkening back to the Apollo era, the first landings were by navigation parlance were pretty gross and inaccurate. I think Apollo 11 overshot the intended landing area by quite a bit, where 16 and 17, well, actually Apollo 12 was a pinpoint landing. They landed next to the crater that contained Surveyor. So with every mission, we're always trying to upgrade our capabilities, provide better autonomous capabilities for the rover. So MSL has this ability to drive auto drive, but it goes very slow. It's very almost never used on the rover because it often gets it into trouble. On Mars 2020, they've upgraded that software and intend to, because of the goals of the mission, to use this auto drive capability to basically set the 2 waypoints and just tell the rover to drive. On MSL, the rover planners actually very meticulously look at the terrain that's coming up and draw the waypoints that the rover will hit on the path that it's driving. So for Mars 2020, we'll look at orbital, pick the 2 waypoints further away, and then let the rover auto drive its way from one waypoint to the next. So that's another upgrade that the Mars 2020 project has. So we're going to be landing at this place called Jezero Crater. And this is a geologic map of, or it's a, sorry, not geologic, it's a topographic map of Mars from about 70 or 80 degrees north to 80 degrees south and 180 east to 180 west. And we're going to be landing at roughly below the datum. So that green colored area, we're going to be landing in that within Jezero crater. Give you better context. So here's Jezero crater context. We're actually down here. This is the Isidis impact basin, and the crater itself is up here. Zoom in a little bit more, and again, this is topography from topography information collected from previous Mars missions. And here's, I believe this is a CTX image composite, and this entire region is Jezero crater in the center. And the white landing ellipse is the area of the crater that Mars 2020 will land somewhere within that ellipse. Again, with the automated landing software, they'll pick a target and then the spacecraft will decide on its own whether that's an optimal location to put the rover on the surface or not. So we really don't want the rover to be set down on top of boulders or in a boulder field that will make it difficult for us to drive out of there. Right now, the Mars Reconnaissance Orbiter high-rise camera will be, we already have imagery from orbit from high-rise of portions of Jezero crater, but that instrument will be taking more high-resolution imagery to give us the best information on the area and where we can drive. And high-rise can create digital terrain models from the observations it captures. So we'll have a rough idea of where we're going to land. And once we get on the surface, then our nav cams and HAZ cams take over looking at the terrain in front of us, creating these digital terrain models and using them to figure out where to drive. So here's a geologic map overlaid Jezero crater and what we believe to have been an ancient lake system and a delta deposit inside the crater. So you see the ellipse overlaid and then a blow up again of, I think this is CTX data, looking straight down at that delta. And hopefully we want to land somewhere just off the delta so that we can sample the ground, the crater floor, and then drive up onto the delta and then up into that nearby inlet valley. This area was selected due to these geologic structures and the hopefully, if it is in fact an ancient lake, that we can find this evidence of life in the rock samples here. And then we overlay it a little bit of geologic mapping from orbit. So there's some volcanics, the red, the olivine, those are volcanics on the crater floor. There's some carbonate material, that's the greenish yellow material that we're really interested in, and the iron, magnesium, smectite, which are mineralogy in the delta. All of these are of interest geologically and also potentially for harboring ancient life or evidence of life there. So this slide is kind of showing, depending on where we land, potential mission profiles of where we're going to be driving around and sampling particular areas. And so the little boxes represent areas that will extensively and intensively study with the instrumentation on board the rover. And then the green and the blue lines, or the green and the red lines, are drive paths as we go from one area to the next. During those drives, of course, if there's something interesting that catches the eye of the science team, we'll potentially stop and collect observations of those interesting features, and then continue on our drive to look at those particular areas indicated by the boxes. Okay. So any questions about, before we go into that, any questions about the mission and the rover itself? And if not, then I'll launch into talking a little bit more about Mastcam-Z itself.
So you guys can unmute yourself if you have a question.
Yeah, Ernest, I got a question, John.
All right.
Ernest, enjoyed your talk so far. What's the life expectancy of the mission? Is it like 90 days, a year, or?
No, the primary mission is just over 1.5 Earth years. But
Oh, okay.
so the primary mission being the metrics by which NASA declares a mission successful the allotted time that we're given to meet those requirements is about 1.5 Earth years, or roughly one Martian year. The lifetime of the rover itself is quite longer than that, as is evidenced by the Mars Exploration Rovers, which everybody goes, oh, they were designed to only work for 90 days. Well, that was a misunderstanding of that was the mission lifetime. The engineers always design spacecraft for to last much longer than the lifetime of the mission. So if MSL is any indication of the lifetime of Mars 2020, similar hardware, in fact, better hardware, the wheels are better designed. We can look to at least 8 or more years on the Martian surface after we've concluded our primary mission.
From the looks of the yellow line, I'm sorry, the green line, it looks like you're covering some pretty rough territory.
It does from orbit, but when you get down into at a higher resolution, there's actually pathways. And one of the things that you don't get to see in this presentation because it would take way too long to get through all the material, is the extensive work that the project has done with geographic information system and the best orbital data that we have to build these high resolution digital terrain models and generate slope maps and terrain roughness and look at the traversability of the terrain and can we actually get from one locale to the next to do the science that we need to do. So while it definitely looks like that's pretty rough terrain, all of this has been studied in great detail by the project to ensure success of the mission and to ensure traversability of the terrain by the rover.
Thank you.
Yeah. Any other questions?
Yeah, on the weather station, Ernest.
Yeah.
You do pictures and is it video also? And is there any sound to it?
There is Meta has a sound component, so we'll actually be able to hear what's going on in the Martian atmosphere at the rover. There are no videos from either Meta or the other instrument, Moxie, though we can take video with Mastcam-Z. And certainly, as is evidenced during MSL, a lot of the instrument will do collaborative imaging. So there are plans for, as an example, Mastcam-Z imaging areas that SuperCam before and after they shoot a rock or a sample with their laser. We could also do video. We've done video on Mastcam of I forget what the MSL SuperCam instrument is, ChemCam. But yeah, so we can take video with Mastcam-Z, but Meta and Moxie themselves don't take video.
Okay, thank you.
Mm-hmm. Any other questions? Okay, well, with that, I'll launch into Mastcam-Z. So again, we're a camera, and the first three, the bolded text are sort of our high level, and they're broken down into more finely worded requirements or goals. But really it's to characterize the overall geomorphology of the area that we are driving through. And that's not only near, but also far away. So we can image, assuming a clear day, to the horizon and tell a lot about the morphology of the area that we're driving through. We can also use Mastcam-Z to assess current atmospheric and astronomical conditions. And so that means things like I mentioned before, these tau observations where we're looking at the sun and looking at the lofted dust in the atmosphere. We can also image occultation. So if Phobos or Deimos are transiting in front of the sun, we can image those events. We can look at other atmospheric information through special observations that we do and use those in conjunction with the information that we'll be collecting from Meta and Moxie to get a much better understanding of the atmosphere. And then provide operational support and context for navigation, contact science, sample selection, extraction, caching, and other parts of the Mars 2020. And I put for operational support, that's really intended to, as part of all of, part of what 3 covers, but also in terms of our team's goal is to actually operate the instrument and provide our expertise to the other science teams working on Mars 2020 and to the rover team that's driving the rover itself. So the team itself is rather large. It's distributed. There are several European team members. We really do, the Mars 2020 team is truly an international team in that we have people all over the globe working both in science and operations. But those are our goals. So Mastcam-Z is comprised of, again, a left and a right. Mechanically, they are identical. They're composed of, if you look at the graphic in the lower left, light shade, focus assembly, a zoom assembly, a filter wheel, and the CCD sensor and electronics box for the camera. These all are built by a company in San Diego called Malin Space Science Systems, and they build a lot of cameras that wind up either in orbit around Mars or on the Martian surface, and also cameras that are in other places in the solar system. The Juno Cam is a Malin instrument. The Lunar Reconnaissance Orbiter camera is a Malin instrument. They're also building new instruments that are going to the Psyche asteroid, also going back to the moon on a Korean spacecraft called KPLO. So they build a lot of cameras. They have a lot of expertise. So this is a heritage design based on the MSL Mastcam. And the major upgrade is the zoom assembly. So we actually have an ability to change the focus, focal parameter of the camera, and either look close in at the area around the rover or look further out to the horizon. So we get 26 to 110 millimeter zoom range. The format's the same as MSL Mastcam. We get 360-degree panoramic view via movement of the mast. We can either command as part of our operation the mast or ride along and take imagery if the mast is being moved for other reasons. The design of the camera undergoes a lot of review. Even though it's a heritage instrument, it still goes through a lot of review. And during the build-out process, problems are encountered, small tweaks are made to the design. All of these are always being checked, cross-checked. So the right-hand side is sort of looking at a cutaway of all of the lenses within the assembly and the light, ray tracing of light path through those lenses as they move back and forth to change the zoom setting of the camera. Now, while both cameras mechanically are identical, they are different in that the filter wheels of the left and the right have different filters in the wheel itself. There is some overlap, and that's for redundancy. So if we lose one of the cameras through mechanical or electronic fault, we can still continue to do the science and complete our science objectives. But there is slight differences so that we can get a little bit better coverage of elemental discrimination as we're looking at looking for signature minerals on the surface and within outcrops on the surface. So so if you look at the table on the left, everything that's coded red are new filter, either filter wavelengths or slightly different parameters for the filters, and they're based on our experience with MSL Mastcam and the goals for the Mars 2020, and looking at those goals, how do we take that existing heritage design and tweak it to meet the design goals for and objective goals for Mars 2020. So we've changed out a few filters, created slightly better error bars on that, and that gives us the ability to find the minerals on the right-hand plot. So while Mastcam-Z is a camera, and we using the filter 0, which has what's called a Bayer pattern. That Bayer pattern basically lets us take an RGB image using a single CCD array on the ground. We can process that out into the individual bands and create the color images that you're used to seeing of the Martian surface. And we do a lot of processing to color balance them so they look as if you were looking through an Earth atmosphere. But the truth is, our science team really doesn't care that much about those pretty pictures. They care about the other wavelengths that are going to help identify the mineralogy and let them do the science that they're looking for. And so Mastcam-Z does something called reflectance spectroscopy, which is in those different wavelengths, we can identify peaks for elements. And those elements, when we convolve them together, can tell us, oh, this element or these peaks are associated with hematite, augite, olivine, percolates, or gypsum, which is going to tell us something about the environment of the outcrop that we're looking at. Well, those two slides were a lot of text, and so we'll throw in some requisite pretty pictures. And these are pictures taken during the science calibration. So when the Malin company built out the instrument, they do a lot of testing to ensure that the cameras are meeting the specification needed to meet the objectives as outlined in the proposal. But to do the science, we have to do a little different kind of testing to ensure we understand the response of the camera system as built. And so you can see in the upper left top corner, those are the actual flight cameras on the work table at Malin Space Science System while we were undergoing this science calibration. And one of the things that one of the tests that we performed was actually looking at the geoboard, or what's called the geoboard. And those are the two top and bottom center images. And that geoboard contains actual rock samples, color samples, so that we can understand the response in wavelengths in the individual filters as we image those different, using the different filters. We know what the color should be, and we can figure out the calibration algorithm to get those colors out of the data set. And the samples that are on the geoboard also match rock types and or mineralogies that we expect to see on the Martian surface. There's little EPO figures, so you can see on the upper left of the geoboard, there's some little Lego people in a Lego Mastcam-Z logo. Those are done by for education and public outreach. And you can see a 3D printed calibration target on the geoboard and the approximate orientation that we would see it when viewing it from the mast on the rover on the surface. So this isn't the only thing we're viewing during the science calibration, but it's one of the more interesting and important one that helps convey to people some of the testing that we do on the ground to ensure when we're getting images back from the cameras on the Martian surface, we can actually process them and understand the information that we're getting out of them. That process was a week-long activity at Malin Space Science System. In the lower right-hand corner is the picture of the conference room that we were using as the war room. All of the people in that conference room are supporting the people. So if you look at the bottom center picture, those three people in the clean room who are actually running the camera, taking the data, all the people who were in the conference room were walking through the procedure, taking notes, doing data processing, reporting results back as we were going through that testing to ensure we got a complete data set, the data set's good, we can, we've got a complete data set, go on to the next. We had something like 50 or 60 different tests that we ran during the science calibration to ensure when we are taking those observations of the Martian surface, we can get the best science out of them. And then at the end, the top upper right picture is a picture looking through the window between that conference room, some of the staff that was there at the very end, the PI is holding the mirror, Andy, who's to the left of the principal investigator, Jim Bell, who led the ASU calibration, and I'm not sure, Alex Hayes is to the right of Jim Bell. He was the science team member who was responsible for the science calibration. And I think the person behind Andy is Tex, who is a Malin Science System employee and who's was operating a camera in the room. All of that happened, again, over a week with countless hours of prep time. In the picture on the lower left-hand corner is actually, we had an engineering model of the cameras. We had them at ASU. That's in our clean room at ASU. And we went through some of the test setup that was going to happen during the science calibration to get experience, learn the process, work through that process. So well over a year and a half of prep work culminated in the week-long activity, very long hours. I think we started shifts at 7 in the morning and ended them close to 10 or 11 at night. And then that did not include all of the post-calibration data reduction analysis that happened by various team members. So a lot of work goes into the building of the cameras, a lot of work goes into the testing of the cameras, all this in preparation to be ready to do the science when we hit the surface of Mars. And operationally, of course, you know, at some point the cameras are delivered to JPL, they're bolted on the rover. The rover in its completely assembled is actually tested even further. I think probably every component on the rover goes through a battery of tests individually, and then as they're added to other components, they go through other batteries of tests. So literally, probably every component on the rover has gone through at least a dozen, if not 2 dozen tests over the lifetime before it's certified, ready for launch and operations. So the big picture on the left is the rover fully assembled in a thermal vac chamber at JPL. The instruments were powered up. We were taking data during the thermal vac testing. If you look at the pictures on the right-hand side, the top one is our Mission Operations Center at ASU. Those ladies are all our operations staff. They're doing our downlink, so they're the ones that are receiving the data, doing the data processing, and providing that to our science team and the Mars 2020, and eventually the general public. And then there's the uplink operations, actual operation of the camera is done by the Malin staff out of San Diego. So our operations are happening in 2 different places. And so we spend a lot of time on the phone with the Malin folks. And that calibration target that I was talking about, that Nomen, you can see in the lower right-hand corner, it's on if you look real closely at the rover, find the back end of the rover, the big barrel that's sort of the dark gray barrel that's sticking straight up, and then kind of come towards the turret. It's kind of washed out in the image, but it's sitting on top of that electronic box that sits up off the top of the rover. And there's actually 2 components. There's the Nomen, and then there's an L bracket that's sitting down on the side. We added that after our experience on MSL with there being a large amount of dust accumulation on the Cal target on that rover. Even though there's magnets embedded in the Cal target, it still gets a lot of buildup of dust. So between the L bracket and the actual Cal target proper, we can hopefully get areas that are both dust covered and dust free to understand the accumulation of dust on the target and how it affects the data that we get back from the camera. So Mars is a very dusty place. There's dust in the atmosphere. It's coming out of the atmosphere, depositing onto the surface of the rover, surface of the rocks. So on Earth, we generally, as a geologist, you're walking around the field, you see something interesting, you walk over, you pick it up, and as a geologist, you kind of go, interesting, and then the next thing you do is you take out your rock hammer and break it, because the outside of the rock isn't what the inside looks like, because it's been weathered, there's dirt on it, accumulation of junk and detritus. So you always want to break that rock open so you can see a nice clean feature of what that rock sample is. Well, we have yet to figure out how to give the rovers a rock hammer to break open things. So the best that we can do is understand when there's dust on the surface, how that changes the observations that we collect, so that we can accurately determine the material that we're looking at. So that's kind of it. I think I pretty much hit my time marks. If you want to know more about Mastcam-Z, we have a website, and more about the rover, you can go to either the JPL website or the NASA website. Both will give you lots of information about the rover, the instrumentation, the mission.